Hey everyone, so today we are doing circular motion and rotation. Again, this 18% is up in the air, okay? So we are starting with circular motion. So uniform circular motion, an object is in a circle moving at a constant speed. Now, big thing to remember, it does not have a constant velocity because it's changing its direction, therefore it is accelerating, okay? So your centripetal acceleration is just your speed squared divided by the radius. Okay, you do not have a tangential acceleration, okay, because your speed's constant, but you are changing your direction. So we did that circular motion lab where you guys were spinning things above your head. Okay, look at that one. And then the circular motion problem in physics really threw me for a loop. Okay. So one thing we can measure is the periods. The period is the time to complete one cycle. Okay, so you got to remember those poi balls. They're actually at school. I don't have them. I can't show them to you. But the poi balls, okay, spinning in the air. The period is just the time it takes to go around once. Your unit is seconds because it is a time. Okay, and then we have frequency is the cycles per second. So this variable is hertz or F, and the unit is hertz. Okay, it is the inverse of period. So if you have a really long period, you have a really short frequency. Okay, and vice versa. Okay, so frequency is how many times you go around in 1 second, or in 1 second. Period is how long it takes to go around once. Okay, so what is love? Baby, don't hurt me, no more. Hey. Okay, so centripetal is called center seeking. So your forces, your net force is always towards the center. Okay, so you'll notice it's towards the center here, but your velocity is tangent. So if you guys remember me standing in the back of the classroom, I let go of the poi ball and it went tangent. Okay, your forces are a vector, okay, because they're forces. Your speed is just the distance over the time. So it's 2 pi r, which is one circle divided by the period. Okay, we also did vertical circles. This right here is a little done. Remember, your acceleration is positive. So at the top, you have gravity and tension going down. They're both positive because they're towards the center. Versus at the bottom, you have tension going up and gravity going down. Tension's positive, gravity's negative because tension's towards the center, gravity is directly away from the center. Okay, so a couple things to note is the minimum speed to get around once, okay, that tension becomes 0 and all you have is your force of gravity. At the bottom, your tension is actually the greatest because it has to fight against gravity. So the graviton ride, we did this problem in class. So it's when you're standing against the wall, your normal force is out and your friction's up. Okay, so you figure out that the minimum value of mu is just rho over v squared. Banked curves, we also did this one in class. So this one's very calculation heavy, so your AP exam is not going to be calculation heavy, but make sure you know why we did certain things. Okay, so all of these are components because the centripetal force is directly to the side. Okay, so we don't break down gravity. Okay, now we move on to angular kinematics. Okay, so this is what we did right after momentum. So for an object to stand up, its center of mass needs to be supported. Okay, so the books, you guys remember walking in and that book was all the way over? Okay, it's because this center of mass is right in the middle, so it's supported by this book. Then the center of mass of both of these is right here. And then the center of mass is here and here. So you can inch them out. Okay, so it's completely over. Okay, your center of mass needs to be supported. Your Leaning Tower of Pisa, your center of mass is right here. Okay, and then it's supported. If the center of mass was over here, it wouldn't be supported, it would fall. So also think about that ruler activity we did where you guys calculated the center of mass of all the rulers and did all those calculations, okay? So then we moved on to angular motion. Okay, so angular kinematics. So big things to know. Bigger the radius, the bigger the linear velocity, okay, tangent position. So the theta, okay, is your angle, it's your displacement. Remember, counterclockwise is positive. Clocks are wrong. Omega is your angular velocity, okay? V is your linear velocity. That's the one, okay, that's going tangent. So remember when I made you guys walk in a circle and you guys were heading to walk in a circle, the person on the further end had to walk faster, okay, because their linear velocity was faster even though you had the same angular velocity. You guys were going through the same angle in the same amount of time, but the person further had to walk more meters in the same amount of time. Okay, so tangential acceleration is how fast you're changing your angular speed. Okay, centripetal acceleration is how fast you're changing your direction. Okay, so these equations are the exact same equations that we learned at the beginning of last school year, okay? Except instead of v, we're using omega. Instead of x, we're using theta. Instead of a, we're using alpha. Okay, time is still the same. Okay, so remember, whatever is a vector in linear is still a vector in angular. Okay, and all of the calculus equations still apply. Okay. Okay, so Newton's first law of rotation, okay, is very similar to his just regular first law. So an object at rest tends to remain at rest, and an object that is spinning tends to spin with constant angular velocity unless it is acted upon by a non-zero net torque, or there is a change in the way the object's mass is distributed. So think of, for that part that's italicized, think of the turntable where you brought it in, okay? That was a change in the way the mass is distributed. So inertia. Okay, just means. So inertia is your tendency to resist acceleration. Moment of inertia is the tendency to resist angular acceleration. Okay, now, luckily, you don't have to memorize these moments of inertia because, okay, it's an open note test. But you do need to know how the moments of inertia are like derived. So think about, why is it that, the rod has one thing at the end versus in the middle, okay? It's how easy it is to rotate it. And you need to know how that easiness to rotate affects other things, okay? So don't memorize these numbers. Don't memorize these equations. You're not going to need them, but know how they change it. Okay, same with the parallel axis theorem. You're not going to need to know how to calculate it. You're going to need to know what changes. Okay, torque. It's a force that causes a rotation. Okay, so you get R cross F, so RF sine theta. Remember when I made you guys walk downstairs and open doors? Okay, that's what we were talking about. How to open a door, easiest, you need the biggest R, okay, biggest F, and your theta needs to be 90 degrees. That's why we do it 90 degrees and don't do it at an angle. So your second law of rotation is the sum of torques equals I alpha. So torque is just RF sine theta, I is your moment of inertia, and alpha is your angular acceleration. So we did this moment of inertia of a pulley where I made you guys calculate the I. Okay, that's what that is. Okay, rotational energy. Which disk wins? Is it the one that's the hoop, or is it the one that's completely filled in? So which one wins and why? You need to know the why. The why is super important. Okay, we're going to fast forward through this because this gets like really slow motion and really intense. Okay, so this black one wins. Its moment of inertia is 1/2 mr squared. The other one is mr squared. So if you have a lower moment of inertia, it's easier to rotate, meaning your linear velocity gets faster. So another way to put this, the black disk, okay, it takes less of the energy. They both have the same potential energy at the top. The black disk takes less potential energy to rotate, so it has more energy to move forward, versus the silver disk, okay, takes more energy to start rotating, and that therefore it has less kinetic energy of linear. Okay, so rolling requires friction. If there's no friction, it can't roll. Friction is what actually causes it to roll. Okay, so you can't always see this picture, but the friction acts right at that contact point. It's static friction. Okay, it holds that little piece of the material. Okay, but your inertia keeps it going forward, so it unsticks, and then the next part sticks. Okay, that's what causes that rotation, that rolling. Angular momentum. Okay, it's conserved, just like linear momentum. Okay, so that blue disk. Okay, that's when we stood there, brought our arms in. That's our change in angular momentum. So think about Kepler's laws. Okay, Kepler's second law is conservation of angular momentum. Okay, so you might have to be able to describe why some planets move faster at certain parts of their orbit. It's because of this angular momentum. Okay, and it's momentum, so therefore it's a vector. Okay, and guess what, guys? We have reviewed everything in AP Physics. Yay! Okay, so please let me know what questions you have today. You do not have to work on that worksheet. We'll do that next week. Okay.